8 times 10 to the 8 meters per second. The second is recorded by the duration of 9,192,631,770 periods of the radiation corresponding to the translation between two hyperfine of the ground state, which are small shifts in the splitting of the energy atoms of the cesium atom 133. So the mole. The mole's amount of substance was contained as many elementary entities as there are atoms. So 12 grams of carbon-12 is 1 mole, which is right here we have Avogadro's number of 6.02214 times 10 to the 23. And I love this picture of 2 moles per liter. Okay, temperature is recorded in kelvins. So the fraction of 1 divided by 273.16 of the temperature of the triple point of water. The triple point of water within the current exact value of the Boltzmann constant. And the triple point of water is, water has 3 different states. You have gas, liquid, solid. And so at a certain pressure, you'll have all 3 states of matter. The amp. So the amp is the constant current if maintained 2 straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in the vacuum, which produce these conductors a force of 2 times 10 to the negative 7 newtons, which is 1 amp. So basically what that is 2 rods placed 1 meter apart, and then you get a certain force there. Candela. Candela is a measurement of luminous intensity in a given direction of a source that emits a monochromatic radiation of frequency of 540 times 10 to the 12 hertz. That is a radiant intensity of the direction of the watt per steradian. I didn't know what a steradian was, so I put a little picture for everyone else that might not know what it is. And then finally, we have the kilogram. So the kilogram is defined by the mass of the international prototype of the kilogram known as IPK. So just so everyone knows, IPK means the international prototype. So does anyone see the problem with IPK? So just in case, it's defined by a piece of metal. This metal is held in France. It's a cylinder that, give me 1 second. It is made out of a platinum iridium alloy cylinder, which is stored in the Bolton Terrace. There was copies made of this alloy cylinder given out to different countries of scientists in different countries of the world. They come back later on and check the difference between the standard that we have there. And the problem is that we've noticed fluctuations in weight. Obviously, IPK is the standard, so regardless if it gains or loses weight, that's the standard, and that's what a kilogram is. So what happens if we lose this piece of metal? What happens if it gets scratched? There's a lot of what ifs. So we need a fundamental constant to help define what the kilogram is. So scientists were looking for a solution. They didn't really know have something that was reliable, repeatable, until we had German physicist Klaus von Kiesling. And I thought that was a pretty cool picture. So he was awarded the Nobel Prize in Physics for the discovery of the quantum Hall effect. He discovered that using thin layer of electrons near absolute zero, when a certain current was applied, a current voltage, that a ratio, a universal value, regardless of the imperfections of the sample, was produced. Here's a picture of this sample that he used. Obviously, you can see that it's pretty dirty, but he was still able to produce his constant here. So why is that important? Well, not even von Kiesling knew what his discovery meant. But here, the National Institute of Standards and Technology, NIST, was able to use that universal constant that was discovered by Van Kiesling to build a balance. This balance uses electrical and mechanical power with a coil and magnetic system that they use to define the kilogram. So the physics, just so everyone knows, I'm currently in physics 151, and some of the physics that they use here for the balance, it's actually physics 152, so I haven't been exposed to some of that material yet, but I'm going to be going over it anyways. So some of the properties, so how it works is it uses the properties of the electromagnetism and constants, and what you have is coil A and coil B that are free floating around a magnet, and a current is then ran through the coil, which interacts with the magnetic field. This strength can then be calibrated and a mass applied to coil A. So I know that's just kind of talk, but here what you have is these two magnets are stationary, and you have this coil that can move up and down. So with a scale, you have two modes. You have a weighing mode and a velocity mode. The weighing mode. So what you're going to have is mass times gravitational constant times upward force of the current in the conductor and magnetic field strength and length of wire of the conductor. The problem that we have here is that it's easily to calculate for I, but not for B times L. So one way around this is using velocity and voltage. Michael Faraday discovered that moving a coil through a magnetic field would generate a voltage. This can then be calibrated in coil A by the up and down motion. So because we're using the same coil in the weighing mode, we can use we can use those numbers in the velocity mode. So here we're going to have a voltage equal to velocity times magnetic field strength times length of wire in the conductor. So again, we see that V times L. So what we can do here is set them equal to each other and solve for M and put a mass in. So the reason why I wanted to do this presentation was because initially I wanted to build a Lego wall balance. The National Institute put out a PDF file where it was open source and anyone can make this build. The build's about a $650 build, and you can measure grams up to 1% relative uncertainty. Unfortunately, I was overambitious, and each little piece of Lego, I didn't know how hard it was to get, and so I didn't have enough time to make the build. But when I take Physics 152, I plan to build this with the help of some other clubs, and my next presentation will be on the Lego wall balance. So, one really piece of exciting news is the redefinition of the kilogram is going to be on the 20th of May. So that's 10 days from now, which I thought was like totally cool with this presentation. So in conclusion, I provided a brief overview of the history of SI units, the problem that we identified with the kilogram, the physics used by the Niskibble balance, and the Lego watt balance for my next build. Are there any questions? Yes, ma'am.
For the Lego watt balance, what is it that makes it actually work? I mean, how does it?
So you have coil A and coil B, and the coil B moves coil A.
Okay.
And then when we have that velocity mode, and you move in coil B at a constant rate, it's able to record it. And so I'm not a programmer or anything like that, but the NIST actually provides all that programming stuff. So all I just need is a computer, some of the circuits and stuff like that, and then I'm able to make the Lego wall balance. Yes.
I have more of a I'm an English major, so this is like totally out of my comfort zone.
Oh.
And I just want want to say that I appreciated how you would like say things in very scientific terms, like those who do understand. But then you'll say like, oh, here's a picture of it. Like for me, it's just like, okay, I don't know what those words mean, but like you explained it really well for those who don't understand.
Thank you. Any other questions? All right, thank you very much.